The question is, could you explain concepts such as elasticity, yielding, etc.? In answering this question, let's start with one of the fundamental things we do in a laboratory in order to find the stress-strain behavior of a material, and it's called material testing, right? So what do? Well, typically this is what we do. We take a small specimen which has a certain length and a cross-sectional area and hook it up to a material testing machine like shown in this picture. We then apply either a tensile force or a compressive force, gradually starting from zero, and then measure the corresponding deformation or displacement on the specimen, right? We calculate the stress on the specimen simply by dividing the force by the cross-sectional area of the specimen. We calculate a strain on the specimen simply by dividing the displacement, delta, by the length of the specimen, L naught, right? Now we plot a relationship between the two, the stress and the strain. The nature of the measured stress-strain relationship depends on the material. By the way, let me also point out that L naught here, the initial length, is also called the gauge length. In a materials class, you will learn different types of materials like viscoelastic material and so on. At this point, for the purpose of this course, it is sufficient for us to consider these two material types. One is called the ductile material, the other is called the brittle material. Aluminum alloy is an example of a ductile material. Cast iron is an example of a brittle material. So what exactly are they? Here is a typical stress-strain behavior of an aluminum alloy, which we know is a ductile material, right? Let's try to understand the stress-strain relationship a little bit first. Point O here is the starting point. So this is the point where the specimen has been hooked up to the machine, but we haven't applied any loading yet, right? Now we gradually increase the load, F, right? Thereby increasing the stress. Now when you do, there's going to be a corresponding increase in the strain. It turns out that for most materials like aluminum alloy, this part right here from O to A is a straight line. But once you hit point A, it turns into a curve. Looking at this from a different angle, the region from O to A is also called the elastic region. This is the region where the material behavior is said to be elastic. So what exactly is the elastic behavior? Well, this is what elastic behavior is all about. You load it up to a certain point and then unload it. The loading stress-strain relationship and the unloading stress-strain relationship coincide with each other. So at the end of this loading-unloading part, there is no leftover strain in the specimen. So you wouldn't even know that the specimen was actually subjected to some kind of loading-unloading program. And of course, you have seen many materials like that in your real life, right? Elastic spring is one of those things, right? But if the loading and the unloading relationships don't coincide with each other, like in the second case, the material is not elastic. It's called elastoplastic. It is obvious that in the second case, at the end of the loading-unloading program, there is a permanent strain, right? Leftover strain in the specimen. And this strain is called the plastic strain, sometimes called the permanent strain. But there is a little bit that we were able to recover, and this part right here is called the elastic strain. So the total strain from here to here consists of two parts, elastic part and a plastic part. Elastic part is the one that we are able to recover, but plastic part is a permanent part. It stays in the material. So coming back to this stress-strain relationship of the aluminum alloy, point A is where that change occurs. In other words, from O to A, the behavior is elastic, but as you go beyond point A, it is no longer elastic. It becomes elastoplastic. In other words, if I were to unload it from a point like that, it's going to go like this. Okay? You're going to end up having a permanent strain. So this point right here, point A, that separates the elastic behavior from the elastoplastic behavior is called the yield point. And the stress at that particular point is called the yield stress or yield strength. Sigma y is a fairly common notation for that, with y denoting yielding, if you will. When we go beyond point A, we know the stress-strain relationship is no longer a straight line, it's a curve, right? But there are two regions in there, region from A to B and then from B to C. Why do we call the region from A to B a strain hardening region? See what happens to the yield stress. Yield stress at this point is sigma y0. Yield stress at this point is sigma y1. Yield stress at this point is sigma y2. This point is sigma y3. This point is sigma y4. I know I'm confusing you, right? Let's dig in a little deeper, okay? This sigma y naught is what we call the initial yield stress. All right, so as long as my applied stress sigma is less than that, we are in the elastic region. The material behavior is going to be purely elastic, right? In other words, I can load, unload from any point between this point and this point. We are not going to have a permanent strain, right? Loading curve and the unloading curve, which of course in this case are straight line, they're going to coincide with each other, right? Let's say I go beyond point O to 1, right? 0 to 1 here, right? And now unload it. Well, this is going to be your unloading curve, all right? It's going to be a straight line, and this straight line is going to be parallel to this straight line right there. Obviously, we are in the elastoplastic region. The behavior from point 0 to point 1 is elastoplastic. So when we unload it, we end up at a permanent strain. This strain right here is permanent strain, right? Now let's reload it from this point, okay? What's going to happen is it's going to go along this line right there until it hits point 1 one more time. And if I go beyond that, it's going to go and join this backbone curve, all right? And it's going to follow that curve. And if I go to point 2 and unload it, it's going to follow a straight line path like this, and this straight line is going to be parallel to this. So all these straight lines are going to be parallel to this. If I go beyond 2, same thing is going to happen, all right? So when I unload it from point 1 and load it back, it doesn't yield until it gets to point 1, right? So what is the stress there? Well, sigma 1. Sigma 1 is greater than sigma y0. So my yield stress has effectively increased. And similarly, if I go from point 1 to point 2, the yield stress increases again from sigma y1 to sigma y2. So you can see from 0 all the way to point 3, which is the peak point on this curve, my yield stress keeps increasing. And this behavior is what is called the strain hardening behavior. On the other hand, you can see from point 3 all the way to this point right there, which we call rupture point, my yield stress has been decreasing, right? So this part is called strain softening behavior. All right, let's also define a few other significant points here. Point B here is the peak point on the curve, right? And this is called the ultimate point, and the stress at that point is called the ultimate strength of the material. Point C here represents the complete rupture of the material, all right? So your specimen is going to break at that point. So this point is called the rupture or a fracture point, and the corresponding stress is called the rupture strength or the fracture strength. Now let's discuss a little bit about brittle materials. The best way to understand the stress-strain behavior of a brittle material is by comparing its stress-strain behavior with that of a ductile material. So here is a comparison of some key features, the features that really set these two materials apart. For brittle materials, first we note that there is no such thing as the ultimate and the rupture points. Both of them coincide, okay? Whereas for ductile material, which we discussed in the previous slide, we know the peak and the rupture points are different from each other, right? Second, we note that the rupture strain for a brittle material is much, much smaller than the rupture strain for a ductile material. If you look at the cross-sectional area on which the test material, test specimen breaks at failure, it looks something like this. So the area of the cross-section on which the failure takes place is very close to the initial cross-sectional area of the specimen. Whereas for a ductile material, this is what happens. As you keep pulling, you know it's not going to fail until the strain gets very large, right? So what happens is, somewhere in the middle, right, the specimen is going to become thinner and thinner and thinner, and this phenomenon is what is called necking. At some point, it's going to fracture, right? The area of the cross-section on which the fracture takes place is usually much, much smaller than the original cross-sectional area of the specimen. The fact that we have a very small strain at failure for a brittle material also implies that the final length of the specimen at failure is very close to the initial length, right? Whereas for a ductile material, the strain at failure is very large, and therefore the final length is much bigger, and provided you are doing a tensile test, right? Final length is going to be much bigger than the initial length. So these quantities are sometimes used to characterize the degree of ductility, if you will. A quantity called percentage elongation is defined like this. So the length at rupture minus the initial length divided by the initial length expressed as a percentage. So this is going to be very small for a brittle material, whereas it could be as high as 20%, 25% for a ductile material. A second quantity, which is based on the area of the cross-section where the failure takes place, is defined like this. This is called percent reduction in area, defined as A naught, which is the initial cross-sectional area, minus AF, which is the cross-sectional area at rupture on the cross-section where the failure takes place, divided by A naught, expressed as a percentage. Once again, this is going to be very small for a brittle material, whereas for a ductile material, this could be as high as 60 to 70%. So this is due to this phenomenon called necking, right? Let's talk about a few additional facts about the stress-strain behavior of materials here. Firstly, the elastic portion of the stress-strain relation is not always linear. Sometimes it could be nonlinear like this. Rubber is a good example of such a material. But for most materials we are typically interested in, like metals, the initial part is, the elastic part is linear. And we call the behavior, the corresponding behavior, as linear elastic behavior, whereas here, if the relationship is not linear, we call this a nonlinear elastic behavior. Number two, for most ductile material, because we have the strain hardening part on the curved portion of the stress-strain relationship beyond yielding, this transition from elastic to elastoplastic is not easily identified all the time. To achieve this in a unique way, this method called the offset method has become pretty standard. So what you do is you draw a line that is parallel to this initial part at a strain of 0.2%, all right, and find the point where this line intersects this curved part. The stress at that point is taken as the yield stress. Number three, not all ductile materials have identical shapes of the stress-strain relations. For example, the stress-strain relationship of the low-carbon steel looks like this. So you can see this is a little different from the stress-strain relationship of the aluminum alloy that we have been talking about so far, right? The differences at this level of finer details are beyond the scope here, so I won't delve into this any further. But the key concept that we have talked about so far, including the yield strength, the ultimate strength, and the fracture strength, are common to all ductile materials.